Okay, so now we are going to start looking at the separation of variables algorithm for solving PDEs. Now, the idea of separation of variables and the eigenfunction expansions that we'll see, we haven't even said eigenfunction expansions yet. We're not really going to get into that until next week. This is sort of a pervasive idea in math. And I'm going to give you kind of a motivation for some of it here. And then in the homework, you can also see kind of another perspective. Once we kind of see where we're going today and on Friday, or I mean, whenever you're watching the videos, well, once we kind of know where we're going, there's faster ways to get to that point. But now I'm going to sort of motivate why we want to get to that point in the first place. So I've rambled enough for now. The only thing that I want to mention, which corresponds to question 1 in the notes, is so far all of our methods for solving PDEs have in some way dealt with converting the problem into an ODE. And that's exactly what we're going to do today. So we're going to be looking at the separation of variables algorithm. I'm going to go through question 2, which is what is a separation of variables algorithm. I'm not going to do that separately. I'm just going to illustrate it by solving this example in question 3. This is a boundary value problem, and we're calling it the heat equation. And I'm going to just introduce what the heat equation is in this problem and then work on solving it in the upcoming videos. So it's the t derivative of u is equal to the double x derivative of u, and x goes from 0 to pi. Okay, you can think about what's going to happen if that pi is replaced with an L instead of a pi. There's just going to be more complicated formulas. I don't want to deal with that for now. Okay, we're going to have an initial condition, u of x0 is equal to f of x. Since we're working on a finite interval, though, we're also going to need boundary conditions, and this will make sense both physically and mathematically. Physically in just a moment, mathematically once we get into the method. We're going to insist that u of 0t is equal to u of pi t, and these are both equal to 0, and this is for t greater than 0. Okay, so what is this modeling? So this, I'm just going to work in the context of the heat equation. So u of xt is equal to the temperature of a rod at location x and time t. In other words, we have a rod, let's say going from 0 to pi. What am I trying to do here? A rod going from 0 to pi. So this is 0. This is pi. We're going to make an assumption, I don't know if I can draw this correctly, that it is insulated laterally. So there's like some insulation going this direction laterally. That doesn't look right, I can't draw. But we're assuming the rod is insulated laterally, so heat can't go up or down. It can only go out, it can only go move left or right, which makes this a one-dimensional problem. Heat's only moving left or right. And we're assuming this condition right here, we're assuming that u of 0t and u of pi t are equal to 0. If I look at my rod, it could either be a rectangular rod or a circular rod. It doesn't really matter as long as heat is not flowing up, or as long as heat can only flow left or right. What I'm saying is that I'm keeping my temperature at the ends of the rod 0. And it doesn't, 0 in what, it doesn't matter which temperature system you're picking 0 to be here. Okay, so this is what we're going to look at. This is what we have. This is the problem that we want to solve. And we want to solve this using the separation of variables algorithm. And I'm going to just label this. Well, I don't know why I'm doing that. You don't need to watch me do that. Okay, so that's the setup. In the next video, actually probably the next several videos, we're going to look at how we can solve this